How did some of the strangest truck experiments ever built quietly shape the design of the vehicles that dominate modern highways today? Detroit, 1968. A truck with no doors. You entered through the windshield. The Dodge Deora's mid-mounted engine and radical body challenged every assumption about what a truck should look like or how it should be used. Subscribe and stay for this full investigation because machines like this, radical experiments on wheels, quietly planted ideas now standard in every truck on your highway. That story begins 30 years earlier with a teardrop-shaped tanker and a 12% fuel saving nobody saw coming. In 1939, while most trucks still wore the sharp edges and flat faces of the previous decade, Dodge's engineers in Detroit were shaping aluminum panels over wooden bucks, coaxing metal into a form that looked more at home in a wind tunnel than on a loading dock. The airflow tanker body was pure teardrop, rounded at the nose and tapering smoothly toward the rear, every curve calculated to slip through the air with less resistance. Instead of the usual boxy tank perched on a separate frame, the fuel tanks were built right into the body, merging cargo and cab into a single, continuous shell. This was a radical break from tradition. The streamlined silhouette was not just for looks. Dodge's own tests, published in the late 1930s, reported a drag coefficient of just 0.31, far lower than the 0.45 typical of the era's standard tankers, over a 5,000-mile route. That translated to a 12% fuel saving, a figure that caught the attention of trade journals and rival manufacturers alike. Aluminum was the key to making the airflow's ambitious shape possible. While most heavy trucks relied on thick steel for strength, the airflow's body used lightweight aluminum panels riveted over a steel frame. This choice shaved hundreds of pounds off the vehicle's curb weight and allowed for more complex curves than stamped steel. The result was a truck that not only cut through the air more easily but also carried more fuel per trip without exceeding weight limits. Building these bodies required new skills. Body shop workers had to learn how to stretch and shape aluminum by hand, using English wheels and custom dies. Each tanker was, in a sense, a piece of industrial sculpture, more labor-intensive than the mass-produced boxes rolling out of other factories, but undeniably striking. The cab itself was just as unconventional. With its rounded windshield, integrated fenders, and low-slung profile, the airflow looked more like a passenger car than a commercial hauler. The design prioritized not only aerodynamics, but also driver visibility and comfort, setting a precedent for later ergonomic experiments. Even the paintwork mattered. Fleet buyers could order their company logos in bold, streamlined lettering, turning the truck into a rolling advertisement as well as a technical showcase. In an era when function usually trumped form, the airflow tanker proved that engineering ambition could reshape both. What started as a sketch in a designer's notebook became a rolling laboratory for ideas that would resurface decades later, long after the last aluminum panel left the body shop. Fleet buyers in the late 1930s faced a decision that went far beyond style. The Dodge Airflow tanker, with its sweeping curves and integrated tanks, promised real-world fuel savings, a 12% reduction over long hauls according to Dodge's own test data. But for petroleum distributors, every new feature came with a price tag. Trade journals from the era noted a clear premium on the airflow. Lightweight aluminum panels, specialized hand-formed bodies, and custom paintwork all drove up costs compared to the standard box-type tankers. For companies running dozens or even hundreds of trucks, that premium was not just a line item, it was a gamble on unproven returns. Production numbers tell the story. While conventional Dodge tankers rolled out in the thousands, only a handful of airflow models ever reached the road. Exact figures remain elusive, but period advertisements and dealer records suggest that the airflow was a rare sight even in major oil company fleets. The extra investment in materials and labor, paired with the need for specialized repairs, limited its appeal to buyers who measured value in cents per mile. Maintenance managers, too, raised concerns about sourcing replacement panels and the risk of downtime if an accident damaged the complex bodywork. For the few companies willing to pay, the airflow became a rolling billboard, a signal of modernity and technical ambition. But for most, the numbers simply did not add up. As the 1940s arrived, the industry reverted to more conventional shapes, favoring simplicity and low cost over aerodynamic flair. The airflow's lessons were not forgotten, though. The drag reduction data and integrated design concepts resurfaced decades later when fuel prices and regulatory pressures forced manufacturers to revisit the same questions about efficiency and value. In that sense, the airflow's brief market life became a case study in how economic realities shape which experiments survive and which become footnotes waiting for their time to come. In the late 1960s, as diesel engines dominated the highways, British Leyland's engineering team set their sights on something that seemed more at home in an aircraft hangar than a truck depot: a turbine power plant. The goal was bold: deliver the kind of high power and smoothness that could move heavy loads with less weight and fewer moving parts than any piston engine. The centerpiece of their effort, the Leyland 2S 350, weighed just 850 kilograms, about half as much as a comparable diesel, yet delivered 350 horsepower at up to 30,000 revolutions per minute. On paper, the turbine's promise was hard to ignore. It could leap from idle to full power in just 4 seconds, offering acceleration and throttle response that diesel drivers could only dream about. Test drivers reported a ride free of vibration, with the turbine's distinctive whine replacing the familiar rumble of a six-cylinder. But as the prototypes left the bench and hit the road, the numbers began to tell a different story. The turbine's fuel consumption at steady highway speeds looked competitive, but the moment it dropped below peak load, efficiency plummeted. In field trials around Manchester, fuel use averaged 30% higher than the diesel trucks running the same routes. The turbine also demanded high-octane aviation fuel and a specialized cooling system, adding complexity and cost. Maintenance intervals stretched longer than diesel, 12,000 kilometers between inspections. But when repairs did come, they required skills and parts few shops could offer. Economic headwinds arrived just as Leyland's engineers were refining the design. The oil crisis of 1973 sent fuel prices soaring, erasing any cost advantage the turbine might have offered. Meanwhile, new emissions rules in the UK and across Europe targeted the turbine's Achilles heel: high nitrogen oxide output. Meeting the limits required water injection systems that added weight and ate into payload. By 1974, after barely a year of field trials, Leyland's finance department pulled the plug. The turbine truck never reached production. Yet the lessons from its brief run, lightweight engines, rapid power delivery, and the challenge of matching new technology to real-world economics echoed through later experiments, from hybrid drivetrains to modern fuel cell trucks. The gas turbine story is a reminder that even the most advanced engineering can be stopped cold by the realities of fuel cost, regulation, and the bottom line. In post-war France, Citroën's engineers set out to capture the imagination of tourists with a vehicle that was as much a sightseeing platform as it was a bus. The result, introduced in 1954, was the Citroën Cityrama, a machine that reimagined the very idea of travel through the city. Instead of the usual rows of small windows, the Cityrama wrapped its upper deck in a sweeping glass dome, curving from waist height all the way over the passengers' heads. This was not just a stylistic flourish. The dome offered a true 180-degree view, eliminating blind spots and turning every seat into a front-row experience. Building that dome was no small feat. Citroën's team used double-glazed safety glass, each pane bonded with rubber gaskets to keep condensation at bay and meet emerging crash safety standards. But more glass meant more heat. On sunny days, the interior could quickly become a greenhouse. To solve this, engineers devised a ducted airflow system. Warm air was drawn from the engine compartment, channeled through thermostatically controlled vents, and exhausted through a roof-mounted outlet. In winter, the process reversed, and engine heat was routed into the passenger area, making the dome surprisingly comfortable even in cold weather. The Cityrama's panoramic ambitions came with trade-offs. The tall, glass-heavy dome raised the center of gravity, so Citroën capped the bus's top speed at 55 kilometers per hour, or about 34 miles per hour. French road test regulations reinforced this limit, citing lateral stability and the added 120 kilograms of unsprung weight from the double-glazed canopy. Tour operators and city officials praised the design for its tourism value, but critics pointed to glare and the risk of overheating on summer afternoons. Despite these concerns, the Cityrama sold in modest numbers across France and Spain, carving out a niche as a moving observatory for city visitors. The influence of the Cityrama's glass dome can be traced through later decades as panoramic roofs and large window cabs became hallmarks of high-end coaches and even some long-haul trucks. The experiment with climate control and visibility set a precedent that comfort and passenger experience could drive design just as powertrains or aerodynamics did. In the Cityrama, the pursuit of a better view forced engineers to rethink structure, safety, and climate, all in service of making the journey itself the main attraction. In the thick of city traffic where every minute counts and curb space is tight, the Fagioli twin-coach delivery van offered a different answer to the problem of moving goods through crowded streets. Developed in the early 1930s, this van was built around a simple but radical idea. Keep the floor as close to the ground as possible so drivers and loaders could step in and out without climbing. The chassis rode just 0.6 meters above the pavement, less than 2 feet. That meant a delivery worker could walk straight from the driver's seat through to the cargo bay, grab a parcel, and step out onto the sidewalk in one fluid motion. No ladders, no awkward stooping, no wasted effort. For companies moving hundreds of packages a day, this low-floor design was not a luxury. It was a labor-saving tool. The twin coach could handle up to 2 tons of cargo, using clever packaging to squeeze maximum space out of a compact footprint. The walk-through layout made sense in dense urban grids, where stopping every block and hustling up and down steps would slow a driver to a crawl. Fleet mechanics and route planners saw clear advantages: faster deliveries, less fatigue, and fewer injuries from repeated climbing. But building a van this way was not easy or cheap. The body relied on a network of complex joints and reinforcements to keep the low floor rigid under heavy loads. Each connection added cost and complexity, making repairs more involved than with a standard box van. Despite these challenges, the Fagioli twin coach left a mark. Its walk-through, low-floor concept vanished for a while, but reappeared decades later in the step vans that became staples for couriers and parcel giants. The logic behind the twin coach, designing for the human workflow, not just the cargo, became a blueprint for the last-mile delivery vehicles that now dominate city streets. The lesson was clear. Sometimes the weirdest solution is the one that makes the work itself easier, even if it takes years for the industry to catch up. In the early 1960s, Chevrolet's engineers tackled a problem that delivery drivers and warehouse crews knew all too well: how to load heavy cargo quickly without expensive lifts or awkward maneuvers. Their answer was the Corvair Rampside, a compact pickup that challenged the standard formula for utility trucks. Instead of a closed-off bed with a tailgate at the rear, the Rampside featured a side panel that folded down to form a ramp. This hinged section, running nearly the full length of the cargo bay, could support up to 1,500 pounds, enough for a loaded pallet, a small motorcycle, or a stack of heavy crates to roll straight in from the curb. At the heart of this innovation was the Corvair's rear-mounted flat-six engine. By shifting the powertrain behind the axle, Chevrolet's team freed up the space beneath the cargo bed. The result was a floor that sat unusually low, just over 2 feet from the ground, making the ramp practical and the loading process far easier than with a conventional pickup. Assembly line workers in Flint, Michigan adapted the Corvair sedan's unibody chassis, reinforcing it to handle the stresses of side loading and the extra weight concentrated near the truck's edge. The ramp side's layout also meant that the cargo area stayed clear of transmission tunnels and drive shaft humps, giving warehouse operators a flat, uninterrupted surface to work with. For small businesses and city fleets, this was a genuine time saver. The ramp could be operated by one person, and the absence of rear-wheel wells meant that odd-shaped loads fit without a struggle. While the ramp side never became a runaway success, the idea of lateral cargo access found new life decades later in side-door delivery vans and tilt-tray trucks. The experiment showed that rethinking the chassis and engine placement could open up new possibilities for how work gets done, even if the market was not quite ready to embrace the change. Launched in 1948, the Ford F-Series set a new standard for what a pickup could be. While other manufacturers chased radical forms or futuristic powertrains, Ford doubled down on durability and adaptability. The original F1 rode on a ladder frame, a simple, rugged backbone that could handle years of hard work, whether hauling farm equipment or navigating city streets. Over the decades, this basic architecture barely wavered, even as engines grew from flathead 5.8 engines to today's 400 horsepower EcoBoost 5.6 engines. The F-Series modular approach, separating cab and bed and offering multiple wheelbases and drivetrains, lets buyers tailor their truck to the job at hand. This formula proved so reliable that by the late 1970s, the F-150 had become the best-selling vehicle in North America, a position it has rarely surrendered since. Ford's approach was evolutionary, not revolutionary. Each generation added incremental improvements, stronger frames, better brakes, more comfortable cabs, and eventually advanced driver aids and hybrid options. Yet the core remained the same, a workhorse platform designed to withstand abuse, easy to service, and inexpensive to build at scale. The 2020 F-150, for example, offers a 5,000-pound gross vehicle weight rating, a 6.5-foot bed, and a payload capacity that rivals some light-duty commercial vans. The latest models pair aluminum bodies with high-strength steel frames, squeezing out more efficiency without sacrificing strength. In the world of experimental trucks, the F-Series serves as the control, the benchmark against which every radical idea is measured. It absorbs the lessons that survive the filter of cost, regulation, and user demand. When aerodynamic fairings, ergonomic cabs, or hybrid drivetrains prove their worth, they find their way onto the F-Series. If not, the workhorse keeps rolling, unchanged. This is how the industry balances risk and reliability by letting the mainstream quietly borrow from the margins, one proven idea at a time. Long-haul trucking in Europe during the 1970s was a test of both machine and human endurance. Regulations capped overall truck length, so every centimeter of space mattered. For most drivers, the cab doubled as an office, kitchen, and bedroom. Yet the typical sleeper bunk was little more than a padded shelf behind the seats. Fatigue was constant, and driver turnover ran high. Into this world rolled the DAF 3300 Space Cab, a Dutch experiment that treated the driver's living space not as an afterthought, but as a design priority. The heart of the Space Cab was its modular sleeper, a detachable pod that could be fitted or removed as needed. This was not a cosmetic tweak. Inside, the cab offered a full 1.8 meters of standing height, enough for most drivers to stretch upright for the first time in their working lives. The module added half a ton to the truck's weight, a significant penalty, but it transformed the cab into something closer to a studio apartment on wheels. Fold-down bunks, thick insulation, and built-in storage turned rest stops into real recovery time. For drivers used to crawling into cramped, sweltering bunks, the difference was immediate. DAF did not just rely on testimonials. They commissioned a human factors study to measure the effect. Over a 12-hour simulated driving cycle, drivers using the space cab showed a 30% drop in measurable fatigue compared to those in standard cabs. The findings rippled through the industry. Carriers began to see that investing in driver comfort could pay off in fewer accidents, better retention, and higher productivity. Engineers, once focused on engines and payload, now had to consider sleep quality and mental alertness as part of their brief. The space cab's influence spread quickly. Other manufacturers followed with high-roof modular sleepers, each pushing the boundaries of what a truck cab could be. Today, standing height cabins, climate control, and ergonomic workspaces are standard across Europe's long-haul fleets. The DAF 3300 did not just give drivers more space. It proved that human needs could drive technical change, and that sometimes the weirdest ideas are the ones that stick. Today, mainstream trucks quietly carry the DNA of yesterday's wildest ideas, proof that innovation often starts at the fringes. As global freight volumes grow and emissions standards tighten, the next leap in truck design may once again come from the unexpected. Progress depends on daring experiments, not just safe bets. The road ahead belongs to those willing to challenge convention. Subscribe to keep discovering the hidden stories that drive engineering forward.